Hey everybody, today I will be talking about molar mass. But first, let's talk about the AMU, or atomic mass unit. Atomic masses, or weights, are the masses of the elements in AMU. So let me write that down. So as you can see down here, atomic mass is the mass of an atom in AMU, or atomic mass units. So if you remember from one video, we defined 12 AMU as the weight of one carbon-12 atom. So this is a carbon-12 atom, and this is exactly equal to 12 AMU. So carbon-12 is used as a standard to label the masses of other atoms because we use carbon-12 as a standard for, 12 atomic mass units. In chemistry, many things have a standard before numbers can be used to quantify the concept. So for example, if we want to find out how many kilograms things are, we need to have a standard for what a kilogram is. And scientists created this object that they defined as exactly 1 kilogram. And every other mass that we measure is based on the fact that the mass of that object is 1 kilogram. So this thing is our standard, and it is preserved under very special conditions somewhere in a laboratory. So now let's talk about something called the average atomic mass. On the periodic table, the average atomic mass is written on the top left side, like right here. So what exactly is the average atomic mass? Well, the word says it all. It's an average of the atomic masses. But it's not that simple. For example, it is not the typical average that we think about. For example, if we want to take the average of 10 and 20, we just add it together and divide by 2. But the average that is used to calculate the average atomic mass is called the weighted average. We will talk about what weighted averages are soon. But for now, let's look at this chart right here. So we measure isotopic abundance, or the abundance of every isotope of an element, with a mass spectrophotometer. And the graph here that is generated from it is called a mass spectrum. So you can tell what element or elements are in the mass spectrum if you look at a periodic table and look at the average atomic masses. So in this mass spectrum that I drew here, the smallest numbers are 79 and 81. And if we look at our periodic table, we clearly see that 79 through 81 falls about at bromine. So therefore, this mass spectrum is showing the mass spectrum for bromine. But what are these other two peaks doing here? Well, to tell you the truth, you can't really measure bromine alone because bromine is a diatomic molecule. It exists as a pair. So when you analyze bromine, you are analyzing it as a pair. So as a result, you have 3 different peaks, and so let me tell you what they are. So first over here, we have to know that bromine can exist as 79 and 81. So that just means that bromine can exist as bromine 79 and bromine 81. 2 isotopes that are very common. So if we think about this, the 158 peak comes from 2 bromines that each have a mass of 79 atomic mass units, or like around there. And 160 comes from a combination of 1Br79 and 1Br81, because 79 plus 81 is 160. And last but not least, the 162 peak comes from measuring the mass of a bromine molecule that consists of 2 bromine 81s. So the bromine 81 has an atomic mass of approximately 81, not exactly, but very, very close. And 81 plus 81 is 162. So that's where our peaks came from. Now, let's talk about isotopic abundance. From this chart, which shows intensity, you can clearly see that the intensity for bromine 79 and bromine 81 is approximately the same. Well, that line isn't even close. It's supposed to be right here. So because of that, we can see that the abundance of both isotopes of bromine are approximately the same. So bromine 79 and bromine 81 are approximately equal in abundance. So that's how you read a mass spectrum. So in charts like these, don't worry about these numbers up here, because in theory, the highest peak will be 100 and everything below it will be based on the 100% intensity. So when we're looking at graphs with intensity, we generally look at the ratios between the bars. So for example, this bar is twice as high as this bar, and these two bars are the same, and these two bars are the same. So we're looking at the heights by comparing them and seeing whether they are the same or they're twice as much, and that tells us the relative abundance. So now let's try to calculate the average atomic mass of chlorine. So down here, I'm going to write two things. Chlorine 35. Oops, that's not right. It's chlorine 35. Chlorine 35 has an atomic mass of approximately 34.968852 atomic mass units. And notice how the 35 and 34.97 are, really close, but they're not exact. So keep a note on that. And chlorine 37 will be equal to, let's see, 36.965903 atomic mass units. So how do we find the average atomic mass? So remember how I told you that the average atomic mass is based on the weighted averages of all the isotopes? Well, a weighted average is different from a typical average, and I'll show you why very soon. So I'm going to tell you the abundances of each of these, and note that these abundances all came from a mass spectrum like this one. So the abundance of chlorine 35 is about 75.77%, and the abundance of chlorine 37 is 24.23%. So notice that since chlorine 35 and chlorine 37 are the main isotopes for chlorine, then these two have to add up to 100%, and they absolutely do if you do the math. So let's go undo all this, and now let's figure out how to do weighted averages. So I would like to first show you what a normal average looks like. In a normal average, you take two numbers and you add them up and you divide by the number of numbers. So there are two numbers, so 10 plus 20 divided by 2 is 15. And you can also write this as saying 50% of 10 plus 50% of 20, and that also equals 15. And the reason why I could write it like this is because when you divide a number by 2, so when you divide a number by 2, you are technically just multiplying it by 0.5. So we can see in this case, each number is multiplied by 0.5, which are the same. Now, this is where a weighted average is different. While normal averages have the number like this number be, the same for each number, weighted averages are different. So let me erase this. So in a weighted average, instead of doing like 50-50, we have to do it based on the isotopic abundance, or the abundance. So in this case, we have to multiply 34.968852 by the abundance, which is 0.7577. And notice how I don't multiply by 0.5, since we are not weighing this number and this number equally. So because they are weighed unequally, I have to multiply it not by the same factor of 0.5, but by something that's based on the abundance. So we could do this for the other number too. So it would be 36.965903 times 0.2423, which comes from the percentage turned into a decimal. So let's multiply these, and let me just erase this first and tell you what the results are when I multiply them. So for our first line, when we multiply 34.968852 times 0.7577, we get a number such as 26.4959. Now, we need to keep track of sig figs. So when we multiply two numbers, we take the lesser sig fig of the two. This number has 4 sig figs. This number has, I think, 8 sig figs. So we have to do 4 sig figs. So we have to underline this to tell us that there are 4 sig figs. And now let's do the second row. So when you multiply 36.965903 times 0.2423, you get a whopping result of 8.9568. And this has also 4 sig figs, so let's underline the 6. And when you add these two together, we will basically get, well, let's see. We want the second decimal place. So when we write our answer of 35.45, see how it has 2 decimal places, because the numbers that we added, well, have a maximum of 2 decimal places, since this is marked at the second decimal place and this is marked at the third decimal place. So we take the lower of the 2, and since this has 2, then, we do 2 decimal places here. So notice how we got the average atomic mass for chlorine, and it apparently turns out to be 35.45. So we have to label the units for this now, and since this is in atomic mass units, since this is just an atomic mass, then the units for this will be AMU. So check out the periodic table. The periodic table says that the average atomic mass is 35.45, just like what we calculated. So this is how you calculate average atomic masses on the periodic table. So now let's look at something different. Let's talk about a concept known as a mole. A mole is just a number. It's one of our SI units. It represents the number 6.022 times 10 to the 23rd. And I think I covered up the 2, so let me just underline it a little below it. Now, why is this number special? Well, if we say a mole of atoms, or 6.022 times 10 to the 23rd atoms, then we get a number of atoms that is measurable in grams. So it takes 10 to the 23rd times 6.022 atoms for the stuff to actually be weighable. So this just shows us how small an atom is. Now let's do an example in real life. 1 mole of pennies will be 6.022 times 10 to the 23rd pennies. That's a lot of pennies, and I think you would be very rich if you had a mole of pennies. So the symbol for a mole is just MOL, not surprising there. So now let's talk about something even cooler. So for every mole of an element or a substance, the number of grams inside 1 mole of the substance is equal to the average atomic mass. So the average atomic mass is equal to the number of grams in a mole of the stuff. So for example, if I had an average atomic mass of 35.45 AMU, which is the average atomic mass of chlorine, by the way, then the molar mass of chlorine, or the amount of grams in a mole of chlorine, will be 35.45 grams. Isn't that cool? So the average atomic mass is equal to the molar mass. Is this a coincidence? Well, I think not, because 6.022 times 10 to the 23rd is a very odd number. And the reason why it's odd is because the scientists chose this number just to make it so that the average atomic mass would be equal to the molar mass. So scientists are pretty clever, and we won't go into why the average atomic mass is equal to the molar mass in this video, but I might publish it in a future video separately. So let's look at how moles, our new concept that we learned, can be applied into what we have learned so far. So far we have learned about reactions and how both sides have the same number of atoms. So in this reaction, 2 molecules of water are being decomposed or broken down into 2 molecules of H2 and 1 molecule of O2. And what happens here is that we have 2 molecules of H2O, so we have, 4 H's and 2 O's being broken down into, 4 H's and 2 O's. So note the conservation of mass. Now, how can we apply moles to this concept? Well, to tell you the truth, we can scale up anything in this world. So for example, let's look up here. If we have $1, and let's just say it takes $1 to make a pound of cheese, then we can scale that up. So we could say, it takes $5 to make 5 pounds of cheese. That makes sense because you're just multiplying by 5. Now, this also applies to this too. If we multiply each of these by the number 6.022 times 10 to the 23rd, then we'll get 1 mole of $1 is equal to 1 mole pounds worth of cheese. So basically you have 6.022 times 10 to the 23rd dollars being converted into 6.022 times 10 to the 23rd pounds of cheese. These two mean the same thing because remember, 1 mole is just 6.022 times 10 to the 23rd. Now, can we apply this into chemistry? Well, of course. So we can scale up this reaction. So instead of having just, small molecules reacting, we can scale this up to, very big things. So if we multiply everything by 6.022 times 10 to the 23rd, we are essentially converting molecules into moles, or in the example we just did, dollars into moles of dollars, or pounds into moles of pounds. So note how 2 moles of H2O come from 2 molecules of H2O when you multiply by, 6.022 times 10 to the 23rd as shown here. So the amount of stuff in this cup is 6.022 times 10 to the 23rd, as much as 2 molecules of water. So, it's a drastic change, and this applies to all 3 of them. So 2 molecules of H2 can be converted to 2 moles of H2 by a conversion factor of that. And 1 molecule of O2 can be converted to 1 mole of O2 by the same conversion factor. So remember, if you have $1, you can convert to 1 mole of dollar by multiplying by 6.022 times 10 to the 23rd, since 1 mole is 6.022 times 10 to the 23rd. So you can think of 1 mole of O2 as 6.022 times 10 to the 23rd molecules of O2. So I'm talking about that. And you can talk about 2 moles of H2 as 6.022 times 10 to the 23rd times 2 molecules of H2. Since remember, we're not talking about just 1 mole, we're talking about 2 moles. So that's why it's multiplied by 2. And the same goes for 2 moles of water. 2 moles of water is the same thing as saying 2 times 6.022 times 10 to the 23rd molecules of water. So all in all, you can look at reactions in terms of molecules or moles. So when you look at a reaction in terms of molecules, then it is very small and we are looking at the atoms. But if you look at a reaction in terms of moles, we're talking about bigger sizes that are observable by the human eye. For example, 2 moles of water is actually a lot of water, and we can actually see 2 moles of water with our very own eyes. So let's now get back to the topic of molar mass and talk about how to find the molar mass of something that's not an element. So before, we found the molar mass of an element by knowing that the molar mass is equal to the average atomic mass, and to find the molar mass of an element, we basically just look at the average atomic mass of an element, and they're equal. So for example, if I wanted to find the molar mass of rhenium, then it would be equal to the atomic or average atomic mass of rhenium, which is 186.21 atomic mass units. So now let's talk about how to find the molar mass of compounds or substances composed of multiple atoms and elements. So in this example, we have sulfuric acid, and let's break this down in order to find its molar mass. So remember, molar mass is equal to the average atomic mass. So keep that in mind when we're doing this problem. So H2SO4 is made up of 2 hydrogens, 1 sulfur, and 4 oxygens. So if we find the atomic mass of each of these elements, then we will be able to add them up to get the atomic mass of the entire thing, which is equal to the molar mass. So let's look at our periodic table, find out what the average atomic masses for these are. So H will be 1.01. I'm going to round to the hundredths place, since in my chemistry class, we typically use periodic tables that have masses that are to the hundredths place and not the thousandths place as we see here. So for simplicity, we will do the hundredths place for all the elements, and unless your teacher or instructor specifies otherwise, then I advise you to stick to 1 decimal place when dealing with atomic weights or molar masses on the periodic table. So let's go back to the question. So we figured out that H was 1.01, and let's go back to find sulfur. Sulfur is 32.06, so let's write 32.06, and oxygen is 16.00. And I didn't need to look at the periodic table because I memorized certain common elements that are often found on, many problems involving molar mass. So the most common elements are hydrogen, carbon, nitrogen, and oxygen. Memorize C, H, O, and N, and you've basically become golden. So let's go back to our problem regarding sulfuric acid. So we have to find the atomic mass of this entire compound by adding up these individual ones. So we have to have 2 hydrogens, so 2 hydrogens times 1.01 atomic mass units each. And then we have to add that to, just 32.06 atomic mass units. And then last but not least, we have to add it to 4 times 16.00 atomic mass units. And if you chug that all into a calculator and keep note of sig figs, you get an answer of 98.09 atomic mass units. And since the average atomic mass is equal to the molar mass, then an average atomic mass of 98.09 atomic mass units will be equal to the molar mass of sulfuric acid, or 98.09 grams per mole. So in a mole of sulfuric acid, we will have 98.09 grams because the average atomic mass was 98.09 AMU. So there are many ways to look at this. Instead of considering these as atomic mass units, we could have, right from the very beginning, assumed that this was 1.01 grams per mole instead of AMU, because if all of these were in units of grams per mole, we could have added it all up and got a final answer in the units of grams per mole, instead of going from AMU to grams per mole. But either one definitely works, so don't worry about whichever method you want to use. But theoretically, both of them work. So if we use the other method, then in 1 mole of H2SO4, we have 2 moles of H, 1 mole of S, and 4 moles of O, and knowing the molar masses for each element. So H would have a molar mass of 1.01 grams per mole, and since we have 2 moles, then 2 moles of H would weigh 2.02 grams. So I know it's getting covered up, but you can read that it's 2.02 grams. And 1 mole of S will just be, well, 32.06 grams, since the molar mass of S is 32.06. And the molar mass of O is 16.00 grams per mole. And since you have 4 moles, then it would be, I think, 64.00 grams. So if you add all these grams together, you will also get 98.09 grams. And that is per mole of H2SO4. So this screen just got very messy, but it's fine. I'm sure you all followed through. So now let's do another problem. So 8 moles of H2O. I want to know how much 8 moles of H2O weighs in grams. So obviously we are going to be converting from moles to grams. So we need a conversion factor. So a conversion factor would be something that has moles on the top and grams on the bottom, or vice versa. So a good conversion factor would be grams per mole, and remember, grams per mole is just molar mass. So the molar mass would be an excellent conversion factor for this problem. So let's figure something out. If we have 8 moles of H2O, and we want to convert it to grams, we have to multiply by the molar mass of H2O. So how do we find the molar mass of H2O? Well, it's just like finding the molar mass for H2SO4. We just have to do a little bit of math. So we know that the molar mass of H is 1.01 grams per mole. And since we have 2 of them, then it will be 2.02 grams per mole. And the O is just 1 O, so it will just be 16.00 grams per mole. And once you add the molar masses of each individual piece, so the molar mass of 2 hydrogens is just 2.02 grams per mole, and the molar mass of 1 oxygen atom is 16.00 grams per mole, then adding up the molar masses of each component will give us the molar mass of the total. So our total here will be actually 18.02 grams per mole of H2O. So let's use this conversion factor for our, problem. So we know 1 mole of H2O has 18.02 grams. So let's multiply this out and let's see, how many grams of H2O we have. So keep a note that this 8 is just 1 sig fig and this has 4. So our answer will have 1 sig fig, unfortunately. So let's take out a calculator and find out what 8 times 18.02 is. So when I took out a calculator, I calculated 144 grams, but we need 1 sig fig. So we have to convert this into something that has 1 sig fig. So we can convert this to scientific notation, first of all. 1.44 times 10 to the second grams, and we want 1 sig fig. So instead of 1.44, we will round down and simply have 1 times 10 to the second grams of H2O. Now I know that's a lame number because it's nowhere as accurate as 144 grams, but in the laws of sig fig, this just has to happen. So, just accept it and go with the flow. So you might be wondering, why are we using the average atomic masses for our molar masses instead of the atomic masses of each isotope? So I'm not going to read this because I want to keep this video under 30 minutes, but read this on your own and I'll give you a few notes. So the molar mass of 35 comes from chlorine 35, and note that it's not exactly 35 because remember, we said that chlorine 35 actually weighs, I guess, about 34.968852 AMU instead of 35, but we're just using 35 for simplicity since it's really close to that number. And so read this, and let me read this part. So the only time we might not use the average atomic mass is if we know the sample has only one isotope. So for example, if all the sample is just Cl37, then we use a molar mass of 37. So that's all for this video. Have a nice day.